Okay, welcome back to part 3 of the lecture. Right, before we start, I'll just clarify something I said earlier. Right, just now we talked about the electron accelerating across two potential plates. Right, just to know if the electron accelerates from the negative plate to the positive plate, right, accelerate because it's attracted to the positive plate. Right, the change in potential is positive, right, because final minus initial is positive, right, but the charge is electron charge, so it's actually a negative sign supposed to be substituted inside. So the change in energy as the electron moves from negative to positive part of the plate is actually negative, right? So if the change in energy is negative, the electron loses electrical potential energy as I move across the plates like that towards the left, right? And this will result in a gain in KE, right? So just now I think I said gain in EPE, which is wrong. It should be loss in EPE, all right? All right, so just to clarify that minor mistake, right? Let's move on. Right. Now, question 5, hope you have time to think it over. Suggest why emitter electrons likely have a range of kinetic energy instead of just the maximum Ke for any one frequency of the electromagnetic radiation. All right. So this again goes back to fundamentally how much you understand the photoelectric equation here, right? The energy provided by a single photon, right? Because the color of the photon is one type of wavelength, one type of frequency. So the energy provided by a single photon is a constant value, HF, right? So for me to be emitted with the maximum KE, I must have the minimum energy required to escape from the metal plate, right? That means I must have exactly work function energy. So to quote the example over here, right? For me to have max Ke, I must be the easiest electron to remove from the metal. Okay, so in this case, in the example given here, it will be the electron here, which is nearest to the surface of the metal, all right? And this electron maybe needs 3 joules to escape versus the 4 joule and 5 joule electron. Okay, so only the 3 joule electron has maximum Ke, right? The 4 joule electron will come out but with 0 Ke, all right? Of course, it's possible to have another level here where the amount of energy required to escape is 3.5 joules, right? So if there's another electron here somewhere in between 3 joule and 4 joules required to escape, let's say 3.5 joules, right? How much energy, how much Ke will we have as it escapes? It will be 0.5 joules because the photon given is 4 joules. All right, okay, all right. So hopefully that sort of gives you an answer to the whole question, right? So the maximum Ke only corresponds to the electrons emitted from the metal surface, which is the easiest electron to remove from the metal, right? But if you interact with other electrons not in the surface, for example, more inside the metal, so they are harder to come out. So the electrons emitted from deeper in the metal will lose energy escaping, and therefore they will not come out with max Ke. All right. And of course, other problems may happen. For example, the electron may collide with other particles when it's escaping, right? And therefore, these collisions reduce the Ke it has available coming out, right? So max Ke is the most ideal case of an electron coming out of a metal, right? And the electron must have the minimum energy required to escape from the metal, right? So likely the electron is at somewhere at the metal surface. Right. Some characteristics of the photoelectric effect. Okay, single photon can only interact with and hence exchange its energy with a single electron. Right. So it's a one-to-one interaction. What this means is that one photon must be absorbed by one electron. Right, and it is also very unlikely, right, and we take it that it does not happen, that an electron simultaneously receives energy from multiple photons. That means because the metal is supposedly so big, right? One photon will likely only hit one electron, and the electron is unlikely to ever receive two photons, right? In fact, we consider this never happens, right? Not all photons get to interact with electrons, and the photoelectrons emitted are emitted in random directions with varying speed, which means that if you look at the setup later on, right, I'll just show you the setup, right? So the electrons emitted from this emitter may not emit in such a manner that is collected by the collector. It actually can emit in some direction over here that never hits the collector, which means it will never register as a current. Right, that's also another possibility. Okay, Ken. So those are the ideas behind Einstein's explanation of the photoelectric effect. Right, so we'll move on to the next part. What happens when incident frequency is less than threshold frequency? Actually, again, we have sort of discussed this idea already, right? There should be no emission whatsoever of electrons from the metal surface, because if incident radiation is less than threshold frequency, then from this equation, right, HF is smaller than 5. Then can the electron ever come out? Answer is no, right? So we've already discussed the idea here, right? So minimum HF must be equal to 5 for the electron to possibly come out. And if that is the case, the electron come out with 0 K, right? But if HF is smaller than 5, electron can never come out because, as mentioned earlier, the electron cannot absorb more than one photon, right? Here, it's extremely unlikely for an electron to simultaneously receive energy from multiple photons, right? That means it won't happen, okay? Right, so what happens instead when the photon is sent with frequency less than threshold frequency? Okay, what happens is there's no emission of electrons from the metal. All right, so the electron absorbed from the photons actually appear as Ke of the electrons within the metal, and this Ke actually just lose electron in the metal ions as they collide, and this heats up the metal. All right, so that's why no electrons are emitted and the metal just gets hot. Right, so this is the basic general ideas, the description that we have talked about already. All right, so I won't talk too much about all these things, right? Because all these things we've discussed already. All right, we'll only talk about this part, right? The illuminated electrode, right, which means it's the emitter, emits photoelectrons with various Ke. The electric field points towards the collector as shown in the above figure. All right, then all electrons are accelerated towards the collector and contribute to photocurrent. That means to say, if this is positive, right, even the electron trying to fly away, as we described earlier, will get dragged back. All right, so making this part positive actually collects all the photocurrent, right, to a maximum value. Right, but if I reverse the electric field, right, that means instead of making this positive, I make this negative, right, this all controlled by the variable power supply. All right, then what happens is that the electrons will actually struggle to hit the collector, because if this is the negative plate, electrons are negative, they should be repelled, right? So I can make this more and more negative until the current gets lower and lower until it eventually approaches 0. Okay, so when I adjust the variable potential difference or variable power supply until the current just nice hit 0, that potential difference in the variable power supply is called my stopping potential. Because this stopping potential must be responsible for actually slowing down the electron with the maximum Ke from hitting the collector. Alright, and actually this Vs, which is stopping potential, right, is actually used to calculate my maximum kinetic energy. Right? Why? Because if I can turn around the electron with the maximum kinetic energy from hitting the collector and just nice hit I equals 0, right? That must mean that the Ke of the electron must just nice be used up just before it reach the collector. That means I can take the Ke, the maximum Ke of the electron, to be equal to EVS, right? Because this is the loss in Ke of the electron, and this is the gain in EPE of the electron. All right, as I go from here to here, right? Because just nice here, my potential difference caused my electron to stop just before I reach the collector, right? So that's why you cannot anyhow adjust this thing. You must adjust until it just nice hit 0. Okay, so by measuring stopping potential, we actually can find max Ke. This from conservation of energy. Right, in your electric fields, you should have learned this concept well, right? And this minimum potential is defined as Vs, right? So it's also called stopping potential. Right, so that's the idea behind Vs, right? I think I'll pull up the applet just to show you how to get Vs lah. Right, so again, this is the same applet, right? I'm just going to pull this to maximum, right? You should see current being detected, right? Yeah, not sure why there's no current, right? Let's try to, yeah, so this is how to pull all the current in, right? Actually, I'm not sure why there's no current. Let me try and see. Maybe I should, okay, there's some current like that. Maybe I shouldn't use zinc. Let me change to sodium. Yeah, this is only higher energy electron, but I want to see all electrons, right? So this is how you can see that if it's 0, right, I should get some current, but if I increase the collector to be more positive, right, by right current should increase, right, by right current should increase, but somehow this app doesn't show that, because I think the electrons are already moving in this direction. Okay, but that's not what's so important. What's more important is I want to drop the potential to negative. So you see now this is positive, I'm going to change it to negative. Okay, so as it become negative, you'll see that the current start to drop. Right, I want to find the 0 point of the current. You can see the electrons starting to get pushed back, right? Because this is a negative plate, so it's repelling the electrons. So only very, very few electrons with the highest energy from here will start to hit this part. Right, so I'm going to try and aim for current 0. I'm pushing it down some more. Roughly here. Okay, I think I cannot get exact, but I think it's roughly 3 volts. Yeah, I think 3 volts. Right, so this supposedly just nice. Maybe I can adjust a bit, but I think this thing is not so refined. Okay, 2.8 also can. Okay, cannot really. Let me try. 2.6 cannot. I think 2.8 is the best I can get. You can see 2.8 just nice. The electron just nice hit. Almost hit. There was one that just hit. So let's try and see highest energy electron only. Does this help? Yeah, you can see just nice almost hit. It's supposed to come as close as possible. Right? So I just nice get current 0. Then I read the potential difference here. Then I can say that, the maximum Ke of the electron coming out of this plate is actually 2.8 eV. Right? Because it's an electron. So it come over here, it must have gain potential energy 2.8 volts. It gain 2.8 volts, and it gain energy equal to 2.8 eV. Alright, so that 2.8 eV, you must realize this is a unit for energy already. Then I can convert to half mv squared to tell me what's the max Ke of the electron that is emitted from here. Okay, so back to the notes. Hopefully you understand what's going on so far. Alright, I'm not going to cover all this because we talked about this, but hopefully you now understand a little bit better. Alright, actually I'll just cover a bit. Okay, so why is photoelectric effect experiment why is Einstein's explanation better? Because if you look at what Einstein say, Einstein say that it's not about intensity, it's about the frequency of light being shone on the metal. As long as the frequency of light is bigger than threshold frequency, which is obviously a function of wave function, threshold frequency is related to the work function of the metal, right? So it depends on the type of metal. But as long as the frequency of light is above the threshold frequency of the metal, right, there will be current. If it's lower, there will be no current. Why? Because even if you increase intensity, right, the number of photons, the energy in each photon is still smaller than the threshold frequency of the metal. So the metal will not emit electron because electron photon interaction, remember, is 1-1. That means the electron can only absorb one photon. And if that one photon is not enough energy to help me escape from the metal, that means equal to my work function, then it doesn't matter whether you change the intensity higher or not, because changing the intensity higher, if you remember carefully, just increase the number of photons. But increased number of photons doesn't mean the electron can absorb more than one photon. If you look at Einstein's theory carefully, he said electron can only absorb one photon, right? So more photon doesn't help me because I cannot absorb more than one photon, right? So the sole determinant of whether photo current of photoelectrons are emitted is actually threshold frequency, right? Then again, there's no measurable time delay, right? Again, this one not so clear in the app, but in reality it's so lah. Even if your intensity is very low, your power supply is very low, as long as the frequency threshold is met, right, the electron will immediately come out because the electron is not going to wait for energy as if it were a wave, right? If you wave, if the power is low, I just wait long enough for the wave to shine at me, then I'll absorb enough energy to escape. But Einstein said that's not the case, right? Einstein said that it's either I just absorb a photon with enough energy to escape, or I don't escape at all, right? And if I can escape, it's immediate. I don't have to wait for me to have sufficient energy to escape. I either take a photon and escape, or I don't, right? So there's no waiting, even at very low power sources. So intensity can be dropped to very low, but the photoelectron emission is still immediate, okay? Finally, stopping potential doesn't depend on intensity, but depend on frequency. Again, this one should be already more or less explained to you. Intensity, again, I said we talked about it, is only affecting the number of photons emitted from the light source. It doesn't affect the energy of each photon. And since electron-photon interaction is 1-1 again, then how much energy I have as kinetic energy, which eventually is measured by stopping potential as discussed earlier, must be solely determined by the frequency of the light. Because electron can only absorb 1 photon of light. So if that photon has higher energy, then I escape the matter with higher kinetic energy. Right, full stop. Alright, so that's how Einstein managed to clear all the experimental issues with this photoelectric effect. Right, this graph, I can take it as, I don't think it's super important nowadays. In the past, it used to be very important. Right, that's why if you look at NX, there will be some graphs like that. Okay, but I will just explain to you what's going on here. Okay, so in this case, this is a current against voltage graph. So as I showed you earlier, right, if voltage is 0, right, my current is somewhere here. Right? If I increase the voltage, I will increase the current slightly because in case some of those electrons that fly away from the collector, right, don't enter the collector, right, I will drag that photoelectron back to the collector, right? Why? Because if the electron, let's say, fly this way, if this thing is positive, then it will actually try and drag the electron back into the collector, which should result in a slight increase in current. Although in the experiment that I did in the applet, it doesn't seem to be the case, but there is a slight increase here. You see this slight increase here? Alright, but if you increase the voltage a lot, it doesn't matter lah. It's still constant because the current is not a function of the voltage caused by the variable EMF. It's caused by photoelectrons. That means electrons coming out because I absorb light, right? So if I double intensity, right, what happens is the number of light particles double, which means there should be a double number of electrons, which means that current should double, right? So it's no surprise that if I double the intensity, double number of light particles, there should be double number of electrons coming out. And that's why this I against V graph, the current doubles here when you double the intensity of the light shone on the emitter, right? But if you look at the stopping potential of these two graphs, can you see it's the same? Because stopping potential does not depend on light intensity. It only depends on the type of frequency of light being shone. And in this case, the type of frequency of light being shone on the emitter is the same. So the stopping potential of the photoelectric effect experiment for the same metal, right? So this whole thing is the same metal and the same type of light being shot. That means one wavelength or one frequency, right? So the stopping potential, whether your intensity is 2I or I, it's the same, right? Because the maximum K is the same, right? So that's what is being said here, right? Yeah, all these things we've talked about it, right? So I won't talk about it too much. Let me just briefly look through. Yeah, we talked about this in some variant form, but I just left this reading part here so that easier for you to read. Sometimes you don't want to read the lecture, you just read your notes. It should be quite readable, right? So quickly do question 6, then I will explain it. Right, pause and do. Okay, we are back. I hope you have taken the time to do question 6. A metal surface is illuminated with a beam of monochromatic electromagnetic radiation, which determines the max speed of photoelectrons that are emitted from the surface. Right, max speed of photoelectrons are determined by EVS, right? So it is dependent on two things like HF, which is the type of light shine, and this, which is the work function, right? So the work function actually affects what? Threshold frequency, right? So this one actually can be written as HF naught, right? So it's two things F and F naught, right? So frequency of radiation and threshold frequency of the metal, right? So these two things are what determines the max speed of the photoelectrons emitted from the surface. Okay, let me see if that's all. Yeah, okay, with that, it ends the first part of the lecture. I'll just briefly cover what we've gone through. We've finished LO, A, and P, right? So understand existence of threshold frequency in photoelectric effect, right? We talked about that. Provide evidence that support the particulate nature of electromagnetic radiation, which is what Einstein suggests. Light is a photon, right, with energy equal HF. That's the particulate nature of electromagnetic radiation. Whereas phenomena such as interference and diffraction provide evidence that support its wave nature. That one we discussed also. A photon is a quantum of electromagnetic radiation. This is the definition of the photon. Okay, recall and use the equation E equal HF for the energy of a photon to solve problems where H is the Planck constant, which is given in your formula sheet. So you don't have to worry about that. All right. Can? So with that, we've closed L, O, A, and B. We'll move on to C, D, and E in the next lesson. All right. See you in the next lecture.